Hello and welcome back to Rest in Science. Tonight, we're going to embark on a gentle journey through our solar system, exploring 50 fascinating facts about the cosmic neighborhood we call home. As you settle into a comfortable position, allow yourself to drift along with these words, letting the wonders of space wash over you like waves of starlight. There's no need to hold on to every detail. Just let the information flow through your mind as you relax more deeply with each passing moment. Take a slow, deep breath, and let's begin our peaceful exploration of the worlds that dance around our sun. Imagine, if you will, that you're floating peacefully in the darkness of space, looking back toward the center of our solar system. The Sun, our brilliant star, contains 99.86% of all the mass in our entire solar system. Picture this for a moment. If you were to gather together all 8 planets, every moon circling those planets, all the asteroids tumbling through the asteroid belt, every icy comet in the distant reaches of our cosmic neighborhood, all the dust, all the gas, everything that exists in our solar system, except the Sun itself, it would account for barely more than 1/10% of the total mass. The Sun is so massive, so overwhelmingly dominant in its gravitational presence, that it holds all of these celestial bodies in their elegant orbits through the pure force of its immense bulk. Consider for a moment that you could fit approximately 1,300,000 Earths inside the Sun's volume. That's not 1,000, not 100,000, but more than 1,000,000 of our entire world, nested within that glowing sphere of plasma. And yet, as you float there in your imagination, the Sun would appear almost gentle, a distant sphere of light that has been burning steadily for 4.6 billion years, providing the warmth and energy that makes life on our planet possible. Now let your mind drift outward from the Sun, past the scorched surface of Mercury, past cloud-wrapped Venus, past our own blue Earth, and settle for a time on Mars, the red planet. Mars, in all its rusty beauty, is home to the largest volcano in our entire solar system. A mountain so vast, it challenges our earthbound understanding of what a mountain can be. This giant is called Olympus Mons, and if you were standing on the Martian surface looking up at it, you would be gazing at a volcano that rises approximately 21 kilometers, or about 13 miles, above the surrounding plains. To put this in perspective, imagine Mount Everest, the tallest mountain on Earth, which reaches approximately 8.8 kilometers above sea level. Now picture stacking 2.5 Mount Everests on top of each other, and you would still not quite reach the summit of Olympus Mons. The base of this magnificent volcano is roughly 550 kilometers across, about the same distance as from London to Edinburgh or from San Francisco to Los Angeles. If you stood at the center of Olympus Mons and looked toward its edge, the volcano would extend beyond the horizon in every direction. The slopes are so gradual, rising at an average angle of only about 5 degrees, that if you were climbing it, you might not even realize you were ascending a mountain at all. You would simply walk for days and days, slowly gaining altitude across a landscape of ancient frozen lava flows, until eventually you would reach the summit caldera, a complex of overlapping craters 85 kilometers wide, where magma once pooled beneath the Martian sky. This peaceful giant last erupted perhaps 25 million years ago, and now it sits silent and dormant, a monument to the geological forces that once shaped Mars into a world of fire and stone. Let's drift for a moment to contemplate the rings of Saturn, those magnificent bands that have captivated human imagination since Galileo first glimpsed them through his telescope in 1610. When you picture Saturn in your mind, you likely see those iconic rings encircling the planet like a cosmic halo. But consider this: despite their vast appearance and their span of over 280,000 kilometers from edge to edge, Saturn's rings are incredibly, almost impossibly, thin. If you were to measure the thickness of the main rings from top to bottom, you would find they average only about 10 meters thick in most places. 10 meters. If you were to scale Saturn down to the size of a basketball, its rings would be thinner than a sheet of paper wrapped around that ball. These rings are composed of countless billions of particles, most of them chunks of water ice mixed with some rocky debris, ranging in size from tiny grains smaller than sand to boulders as large as houses, all orbiting Saturn in an intricate cosmic dance. Each particle is essentially a tiny moon, following its own orbital path around the planet, and together they create those beautiful, luminous bands that shimmer in the sunlight. The rings are thought to be relatively young in cosmic terms, perhaps only 100 to several hundred million years old, meaning they may have formed during the age of dinosaurs on Earth. Scientists aren't entirely certain how they formed, though one leading theory suggests they might be the remains of a moon that ventured too close to Saturn and was torn apart by the planet's powerful tidal forces, its shattered pieces spreading out into the glorious ring system we see today. Journey with me now to the outer reaches of our solar system, to a place so distant that sunlight, which takes only about 8 minutes to reach Earth, takes more than 5 hours to arrive. Here, in this cold and dimly lit realm, we find Neptune, the windiest planet in our solar system. Allow yourself to imagine for a moment the fierce, supersonic winds that scream across Neptune's atmosphere, reaching speeds of up to 2,000 kilometers per hour, or about 1,200 miles per hour. These are winds nearly 9 times faster than the most powerful hurricanes ever recorded on Earth. Winds so violent they could carry you from New York to Los Angeles in little more than 2 hours if such a journey was somehow possible. And yet, here's the paradox that makes this fact so fascinating. Neptune receives only about 1/900th of the sunlight that Earth receives, meaning it gets less than 1% of the solar energy that bathes our world. On Earth, our weather systems, our winds, our hurricanes all derive their energy from the sun's heat. But Neptune, sitting in the frozen outer darkness of the solar system, 30 times farther from the sun than Earth, somehow generates these incredible atmospheric storms and winds despite receiving so little solar energy. Where does this energy come from? The answer, scientists believe, lies within Neptune itself. The planet appears to have a powerful internal heat source, generating more than twice as much energy as it receives from the sun, though the exact mechanism remains something of a mystery. This internal heat drives convection in the planet's atmosphere, creating turbulent weather systems and those extraordinary winds that rage endlessly across this deep blue world. If you could somehow survive in Neptune's atmosphere, perhaps floating in some imaginary protective vessel, you would witness storms larger than Earth itself, massive dark spots that appear and disappear over months and years, and clouds of methane ice that race around the planet at speeds that make our earthly winds seem like gentle breezes. Take a slow breath and picture this distant, dynamic world, a realm of incredible energy and motion in the quietest, darkest corner of our planetary family. Let your thoughts drift now inward, back toward the sun, back to the realm where Earth resides. But pause for a moment at our own Moon, that familiar companion that has hung in our night sky throughout all of human history. Here's a fact that might surprise you. The Moon is gradually moving away from Earth, slowly, steadily, almost imperceptibly, but measurably nonetheless. Each year, our lunar companion drifts approximately 3.8 centimeters, or about 1.5 inches, farther from our planet. Now, 1.5 inches per year might not sound like much, and indeed, in the span of a human lifetime, the Moon's distance barely changes in any noticeable way. But consider this process over vast stretches of time. Over the course of 100 million years, the Moon will have receded by 3,800 kilometers, roughly the distance from New York to London. This gradual separation happens because of the gravitational interaction between Earth and the Moon, specifically through the mechanism of tides. The Moon's gravity pulls on Earth's oceans, creating the tidal bulges we experience as high and low tides. But Earth is rotating faster than the Moon orbits, which means these tidal bulges are carried slightly ahead of the point directly beneath the Moon. These offset bulges then pull back on the Moon through their own gravity, and this pulling force acts like a gentle tug that gradually accelerates the Moon in its orbit. As the Moon speeds up, orbital mechanics dictate that it must move to a higher, more distant orbit, and so it slowly spirals outward. At the same time, this gravitational interaction is slowing Earth's rotation, making our days gradually longer. 4 billion years ago, when the Moon was much closer and Earth much younger, a day on our planet lasted only about 6 hours. Now, our days are 24 hours long, and they're still getting longer by about 1.7 milliseconds per century. Billions of years in the future, if nothing else interferes, Earth and the Moon will become tidally locked, with Earth always showing the same face to the Moon, just as the Moon now always shows the same face to Earth, and the Moon will have drifted so far away that it will appear significantly smaller in our sky than it does today. But for now, for the time frame of human civilization, and indeed for many millions of years to come, our Moon remains our steadfast companion, hanging in the sky at just the right distance to create total solar eclipses, to light our nights and to stir our sense of wonder. Pre-ake. Bre-ake. Point. Consider now the asteroid belt, that vast ring of rocky debris orbiting the Sun between Mars and Jupiter. When many people imagine the asteroid belt, influenced perhaps by dramatic scenes in science fiction movies, they picture a dense field of tumbling rocks so crowded that a spacecraft would have to weave and dodge constantly to avoid collision. But the reality of the asteroid belt is far more peaceful, far more empty than these fictional portrayals suggest. Imagine, if you will, taking all the asteroids in the belt, every single rocky body from the largest, Ceres, which is nearly 1,000 kilometers across, down to the smallest pebbles, and gathering them all together into one mass. If you did this, the total mass of all these asteroids combined would be less than 4% of the Moon's mass. In fact, all the asteroids together would form a body approximately 1,400 kilometers in diameter, smaller than our Moon. Now imagine spreading this relatively small amount of material across a vast, donut-shaped region of space. A region that extends from roughly 300 million kilometers from the Sun to about 500 million kilometers from the Sun, and spreads vertically about 100,000 kilometers above and below the plane of the solar system. The result is an almost unimaginably sparse distribution of material. If you were in a spacecraft traveling through the asteroid belt, you would most likely see nothing at all in any direction except empty space and distant stars. The average distance between asteroids is about 1 million kilometers. That's roughly 3 times the distance from the Earth to the Moon. You could travel through the asteroid belt for days or weeks without coming anywhere close to an asteroid. In fact, we've sent numerous spacecraft through the asteroid belt, missions to Jupiter, Saturn, and beyond, and not one has ever had an unexpected collision with an asteroid, because space is simply so vast and the asteroids so few and far between. This is a reminder of one of the fundamental truths of our solar system. Despite all the planets, moons, asteroids, and comets it contains, our cosmic neighborhood is predominantly empty space, vast distances filled with nothing but the occasional photon of light from distant stars, traveling endlessly through the void. Let's turn our attention now to Venus, that brilliant evening and morning star that has inspired poets and lovers throughout human history. Venus, cloud-wrapped and mysterious, is often called Earth's twin because the two planets are remarkably similar in size and mass. Venus has a diameter of about 12,100 kilometers compared to Earth's 12,700 kilometers, making it only about 5% smaller than our world. And yet, despite this similarity in size, Venus is perhaps the most inhospitable place in our inner solar system, a hellish world where conditions are so extreme that no spacecraft has survived on its surface for more than a couple of hours. The atmospheric pressure on Venus's surface is approximately 92 times greater than Earth's atmospheric pressure at sea level. Imagine being crushed by a weight equivalent to being almost 1 kilometer deep in Earth's oceans, and you begin to understand the immense pressure that exists at Venus's surface. But the pressure is only the beginning of Venus's harsh environment. The planet's thick atmosphere, composed primarily of carbon dioxide with clouds of sulfuric acid, creates a runaway greenhouse effect that has raised surface temperatures to approximately 470 degrees Celsius, or about 880 degrees Fahrenheit. This is hot enough to melt lead, hot enough that if you could somehow place a spacecraft on the surface, the metal would begin to glow red with heat. In fact, Venus is actually hotter than Mercury, despite being almost twice as far from the Sun, all because of that crushing, heat-trapping atmosphere. And consider this: while a day on Earth lasts 24 hours, a day on Venus, the time it takes for the planet to rotate once on its axis, lasts 243 Earth days. Even more remarkably, Venus rotates in the opposite direction to most other planets in the solar system, a phenomenon called retrograde rotation. If you could stand on Venus's surface and somehow survive the heat and pressure, you would see the sun rise in the west and set in the east. A year on Venus, the time it takes to orbit the sun, is only 225 Earth days, which means that a day on Venus is actually longer than a year on Venus. The planet completes an orbit around the sun before it completes a single rotation on its axis. Scientists still aren't entirely certain why Venus rotates backwards or why it rotates so slowly, though theories suggest it might have been struck by a massive object early in its history, or that gravitational interactions with the sun and its thick atmosphere have gradually slowed and reversed its rotation over billions of years. Picture yourself now, drifting through space toward the largest planet in our solar system, Jupiter, a gas giant so massive that all the other planets in the solar system could fit inside it with room to spare. Jupiter has a mass more than twice that of all the other planets combined, and it exerts a gravitational influence that has shaped the architecture of our entire solar system. But let's focus on one particular feature of this giant world: the Great Red Spot, a storm so large and so long-lived that it has been raging for at least 350 years, possibly much longer. Imagine a hurricane on Earth, but instead of lasting days, or perhaps weeks, it continues for centuries. The Great Red Spot is an anticyclonic storm, meaning it rotates in the opposite direction to hurricanes on Earth, with wind speeds at its edges reaching up to 432 kilometers per hour, or about 270 miles per hour. The storm is enormous, large enough that you could fit approximately 1 to 2 Earths side by side within its swirling clouds. When astronomers first observed the Great Red Spot through telescopes in the 17th century, it was even larger than it is today, big enough to fit 3 Earths across its width. Over the past 150 years, the storm has been shrinking, though scientists aren't entirely sure why. As of recent observations, it continues to decrease in size, though it remains a massive and powerful feature of Jupiter's dynamic atmosphere. The storm's distinctive red color comes from complex chemical reactions involving phosphorus, sulfur, and organic compounds being dredged up from deeper in Jupiter's atmosphere and then altered by ultraviolet light from the sun. As you imagine this great storm, picture it churning endlessly in Jupiter's turbulent atmosphere, a feature that has existed longer than the United States has been a country, longer than the Industrial Revolution, longer than many nations have existed. A reminder that the timescales on which planetary processes operate dwarf the entirety of human civilization. Break. Point. Let us drift now to Mercury, the smallest planet in our solar system and the closest to the Sun. Mercury is a world of extremes, a place where temperatures swing more dramatically than anywhere else we know. During the day, when the sun beats down on Mercury's surface, temperatures can soar to approximately 430 degrees Celsius, or about 800 degrees Fahrenheit, hot enough to melt zinc and lead. But here's what makes Mercury's temperature variation so extraordinary. At night, without any atmosphere to trap heat, temperatures plummet to approximately negative 180 degrees Celsius, or about negative 290 degrees Fahrenheit. This means that Mercury experiences a temperature swing of more than 600 degrees Celsius between day and night, an extreme variation unlike anything found on any other planet in our solar system. On Earth, our atmosphere acts like a blanket, redistributing heat and moderating temperature extremes. Even in the most extreme desert locations on Earth, temperature variations between day and night rarely exceed about 40 degrees Celsius. But Mercury, with almost no atmosphere to speak of, just an extremely thin exosphere of atoms blasted off the surface by solar radiation and meteorite impacts, has no such protection. The heat of the day radiates directly into space as soon as the sun sets and temperatures drop precipitously. And Mercury's day is long, very long. The planet rotates so slowly on its axis that one day on Mercury, from one sunrise to the next, lasts 176 Earth days, or about 2/3 of a Mercurian year. This slow rotation means that any spot on Mercury's surface experiences about 88 Earth days of continuous sunlight, followed by 88 Earth days of continuous darkness. Imagine standing on Mercury's surface, watching the sun crawl across the sky so slowly that it would take weeks for it to move from the eastern horizon to directly overhead, heating the rocks beneath your feet to temperatures that would melt metal, and then watching it equally slowly descend toward the western horizon, followed by months of darkness and cold, more extreme than anywhere on Earth. And here's one more remarkable aspect of Mercury. Despite being the closest planet to the Sun and having surface temperatures that reach extraordinarily high levels during the day, there is water ice in permanently shadowed craters at Mercury's poles. These craters, located at the planet's polar regions, never receive direct sunlight because Mercury's axis is almost perfectly perpendicular to its orbital plane. In these eternally dark crater floors, temperatures remain cold enough that ice, delivered perhaps by comet impacts over millions of years, can survive indefinitely, creating deposits of frozen water on one of the hottest planetary surfaces in the solar system. Now let your mind expand outward to contemplate the true scale of our solar system, because here's a fact that might fundamentally shift your perspective on cosmic distances. If you traveled at the speed of light, the fastest speed possible in our universe, a speed at which you would circle Earth's equator more than 7 times in a single second, it would still take you about 5.5 hours to travel from the Sun to Pluto, the most famous of the dwarf planets in our outer solar system. Light from the Sun reaches Earth in approximately 8 minutes and 20 seconds, traveling across about 150 million kilometers of space. This distance from the Sun to Earth is called 1 astronomical unit, or AU, and astronomers use it as a convenient measuring stick for distances within our solar system. Neptune, the farthest planet from the Sun, orbits at an average distance of about 30 AU, meaning it's 30 times farther from the Sun than Earth is. But even Neptune isn't the edge of our solar system. Beyond Neptune lies the Kuiper Belt, a region of icy bodies that includes Pluto, extending from about 30 AU to roughly 50 AU from the Sun. And beyond the Kuiper Belt, even farther out, there's the scattered disk and eventually the Oort cloud, a vast spherical shell of icy bodies that marks the true outer boundary of the Sun's gravitational dominion, extending perhaps 100,000 AU from the Sun, or about 1.5 light years. To put this in perspective, consider the Voyager 1 spacecraft launched in 1977, currently the most distant human-made object from Earth. After traveling for more than 45 years, Voyager 1 is now about 160 AU from the Sun, and it has crossed into interstellar space, the region between stars. But even at this incredible distance, Voyager 1 has not yet truly left the solar system in the sense of escaping the Sun's gravitational influence. It won't reach the inner edge of the Oort cloud for another 300 years, and it won't fully clear the Oort cloud for another 30,000 years. Our solar system is vast almost beyond comprehension, a bubble of the Sun's influence stretching trillions of kilometers into space. And we have explored only the tiniest fraction of it. Consider the moons of Jupiter, and among them, let's focus on Europa, a world that has captured the imagination of scientists searching for extraterrestrial life. Europa is slightly smaller than Earth's moon, with a diameter of about 3,121 kilometers, and its surface is one of the smoothest in the solar system. When you look at images of Europa, you see a world that appears to be covered in ice, crisscrossed with long, dark streaks and cracks, giving it an appearance somewhat like a cracked eggshell. But it's what lies beneath that icy surface that makes Europa so fascinating. Scientists believe that beneath Europa's frozen crust, which may be between 15 to 25 kilometers thick, there is a global ocean of liquid water, an ocean that contains more than twice the volume of all of Earth's oceans combined. Picture this: a moon smaller than our own, orbiting far from the Sun in the cold outer solar system, yet harboring beneath its icy shell an ocean of liquid water that has persisted for perhaps billions of years. How is this possible? The answer lies in tidal heating. Jupiter's immense gravity pulls on Europa, and the gravitational tug from Europa's neighboring moons, Io and Ganymede, causes Europa's orbit to be slightly elliptical rather than perfectly circular. As Europa moves closer to and farther from Jupiter in its orbit, Jupiter's gravity flexes and squeezes the moon, much like repeatedly bending a paperclip back and forth. This constant flexing generates heat through friction in Europa's interior, enough heat to keep a vast ocean liquid beneath the ice. This ocean, if it exists as strongly suspected, would be in contact with a rocky sea floor, and where there is liquid water, energy, and chemistry involving rock and water, there is the possibility of life. On Earth, we find life in the most extreme environments wherever liquid water exists, even in the deepest ocean trenches, in water trapped kilometers beneath the ice, in Antarctica, in boiling hot springs, and in frozen environments. The discovery that Europa likely has conditions that could support life, warm liquid water in contact with rock, possibly with hydrothermal vents similar to those found on Earth's ocean floor, has made this small moon one of the primary targets in humanity's search for life beyond Earth. Priek. Mercury takes its name from the Roman messenger god, Venus from the Roman goddess of love and beauty, Mars from the Roman god of war, Jupiter from the king of the Roman gods, Saturn from the Roman god of agriculture and time, Uranus from the ancient Greek god of the sky, and Neptune from the Roman god of the sea. But Earth, our planet, derives its name from the Old English word eartha and the Anglo-Saxon word erda, which simply mean ground or soil. The word Earth is at least 1,000 years old and possibly much older, with cognates in many Germanic languages. In German, it's Erde, in Dutch, Aarde, in Scandinavian languages, Jord. These words all refer to the ground, the soil, the land itself, a simple, grounded name that reflects humanity's perspective for most of our history as a species tied to the land beneath our feet. It's only in the last few decades since we've been able to leave our planet and look back at it from space that we've truly appreciated Earth, not as ground beneath us, but as a planet among planets, a world floating in space. And our planet is remarkable in so many ways that it's worth taking a moment to appreciate them. Earth is the only world we know of where liquid water exists stably on the surface. This water, covering approximately 71% of Earth's surface, is absolutely critical to life as we know it. Earth is the only planet in our solar system with plate tectonics, the process by which the planet's crust is broken into moving plates that slowly shift, collide, and slide past each other, creating mountains, earthquakes, and volcanic activity. This geological activity is crucial for recycling nutrients, regulating the climate through the carbon cycle, and maintaining the magnetic field that protects us from harmful solar radiation. Earth is the only planet with an oxygen-rich atmosphere, a direct result of photosynthetic life that has been producing oxygen for billions of years. And Earth is, as far as we know, the only planet that harbors life, though our exploration of other worlds is still in its infancy. As you rest and relax, take a moment to appreciate the extraordinary nature of this world we call home, this oasis of life and water and dynamic geology floating in the vast darkness of space. Imagine yourself now approaching Saturn's moon, Titan, the second largest moon in our solar system and the only moon known to have a substantial atmosphere. Titan is larger than the planet Mercury, with a diameter of about 5,150 kilometers, and it is absolutely unique among moons. When you look at Titan, you can't see its surface directly because the moon is shrouded in a thick orange-brown atmosphere composed primarily of nitrogen, the same gas that makes up most of Earth's atmosphere, but with significant amounts of methane and traces of other organic compounds. This atmosphere is denser than Earth's, with a surface pressure about 1.5 times what we experience at sea level on our world. But what makes Titan truly extraordinary is what's on its surface. Titan has weather, clouds, rain, rivers, lakes, and seas, much like Earth. But instead of water, Titan's hydrological cycle is based on methane and ethane. The temperature on Titan's surface is approximately negative 179 degrees Celsius, or about negative 290 degrees Fahrenheit, cold enough that water ice is as hard as rock, and methane, which on Earth exists as a gas, can exist as a liquid and even rain from the sky. Picture, if you will, standing on Titan's surface. Above you, thick orange clouds drift across a hazy sky, and through the haze, you can barely make out the shape of Saturn, massive and magnificent, hanging in the heavens. The light is dim, about 1% of the sunlight we receive on Earth, because Titan orbits more than 1 billion kilometers from the Sun. Around you stretch landscapes of water ice and organic materials sculpted by wind and liquid methane into dunes, river valleys, and shorelines. In some regions, you would find lakes and seas of liquid methane and ethane, bodies of liquid hydrocarbon with waves lapping at their shores. The largest of these, Kraken Mare, is larger than the Caspian Sea on Earth, a vast sea of liquid natural gas at temperatures where water would be solid as stone. Rain occasionally falls from Titan's clouds, not water droplets, but drops of liquid methane, and these drops are much larger than raindrops on Earth because of Titan's lower gravity and denser atmosphere. A raindrop on Titan might be several millimeters across and would fall gently, almost dreamily, to the surface. Scientists believe that Titan is perhaps the most Earth-like world in our solar system, not in terms of conditions suitable for Earth life, but in terms of having active geology, weather systems, erosion, and a dynamic surface. And like Europa, Titan may harbor a subsurface ocean of liquid water beneath its icy crust, heated by tidal interactions with Saturn, making it another possible location to search for life in our solar system. Consider now the concept of planetary migration, a fascinating aspect of how our solar system formed and evolved. When scientists first began discovering planets around other stars in the 1990s, they found something surprising. Many of these exoplanets were massive, Jupiter-like worlds orbiting very close to their parent stars, much closer than Mercury orbits our Sun. This was puzzling because massive gas giant planets like Jupiter form far from their stars, in the cold outer regions of planetary systems where ice and gas are abundant. The discovery of these hot Jupiters orbiting close to their stars led scientists to reconsider the history of our own solar system and to develop the theory of planetary migration. According to this theory, planets don't necessarily stay in the orbits where they formed. Instead, gravitational interactions with the disk of gas and dust from which they form, as well as gravitational interactions with other planets, can cause planets to move inward or outward over time. In our solar system, evidence suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune formed in different positions than where we find them today, and then migrated to their current locations over hundreds of millions of years. One model, called the Grand Tack hypothesis, suggests that Jupiter initially formed farther from the Sun than it is today, then migrated inward toward the inner solar system, only to be pulled back outward by gravitational interactions with Saturn. This inward, then outward migration would have had profound effects on the rest of the solar system, potentially scattering material and preventing a planet from forming in what is now the asteroid belt. Another model, the Nice model, named after the French city where it was developed, suggests that the outer planets formed much closer together than they are now, and then, about 4 billion years ago, underwent a period of rapid migration triggered by gravitational resonances. This migration would have sent Uranus and Neptune flying outward, scattered the Kuiper belt, and sent a shower of comets and asteroids careening through the inner solar system, causing the late heavy bombardment, a period when Earth, the Moon, and other inner solar system bodies were heavily cratered by impacts. These theories remind us that our solar system is not static, not frozen in the configuration we observe today, but rather a dynamic system that has evolved over billions of years and continues to change, albeit on timescales so long that they're imperceptible to human observation. Let your mind drift to the smallest particles in our solar system, the cosmic dust that pervades the space between planets. Every day, approximately 100 tons of interplanetary dust and small particles fall onto Earth's atmosphere. Imagine that. 100 tons every single day, a gentle rain of cosmic material constantly falling toward our planet. Most of these particles are incredibly tiny, smaller than a grain of sand, and they burn up completely as they enter the atmosphere at tremendous speeds, creating the brief, beautiful streaks of light we call meteors or shooting stars. This cosmic dust comes from various sources. Some of it is debris from comets that have passed through the inner solar system, leaving trails of particles in their wake. When Earth's orbit intersects with these trails, we experience meteor showers, those times of the year when dozens or even hundreds of meteors per hour streak across the sky. Other dust particles come from collisions in the asteroid belt, where rocky bodies occasionally impact each other, sending sprays of debris out into space. Some particles have been drifting through space for millions or even billions of years before finally spiraling down toward Earth under the influence of various forces, including solar radiation pressure and gravitational interactions. When these particles hit Earth's upper atmosphere at speeds of anywhere from 11 to 72 kilometers per second, the friction with air molecules causes them to heat up to thousands of degrees, vaporizing completely and leaving a glowing trail of ionized air behind them. A very small fraction of larger particles, perhaps a few meters or larger, survive the passage through the atmosphere and reach the ground as meteorites. And scientists treasure these fragments of space, rock, because they provide direct samples of material from asteroids and, very rarely, from the Moon or Mars, blasted off those worlds by ancient impacts and later captured by Earth's gravity. Every year, a few handfuls of Martian meteorites are found on Earth, rocks that were once part of the red planet's surface, ejected into space by a massive impact, and then wandered through the solar system for millions of years before finally landing on our world. But most of the cosmic material that falls to Earth is dust, silent, invisible, a constant gentle rain from space that becomes part of our world, settling into the oceans, onto the land, integrating seamlessly into Earth's geology. Over billions of years, this steady accumulation of cosmic dust has added significant mass to our planet, and continues to do so. A reminder that Earth is not isolated in space, but constantly interacting with the solar system around it. Take a moment now to consider the extraordinary nature of Earth's moon in relation to our planet. The moon is unusually large compared to Earth, with a diameter about 1/4 that of Earth's diameter. This ratio of moon size to planet size is much larger than for any other planet in the solar system, except for Pluto and its large moon Charon, which are sometimes considered a double dwarf planet system. Most moons in the solar system are tiny compared to the planets they orbit. Jupiter's largest moon, Ganymede, has only about 1/27th of Jupiter's diameter. Mars's moons, Phobos and Deimos, are just small captured asteroids, barely large enough to be round. But Earth's moon is substantial, massive enough to have significant gravitational effects on our planet. This large moon stabilizes Earth's axial tilt, preventing it from varying wildly over time. Without the moon, Earth's tilt could vary from nearly 0 degrees to 85 degrees over millions of years, causing dramatic climate shifts that would make the development of complex life much more difficult. The moon also creates our tides, the rhythmic rise and fall of ocean levels that occur twice each day as the moon's gravity pulls on Earth's oceans. These tidal zones, areas that are alternately covered by water and exposed to air, are thought to have been crucial environments for the evolution of early life on Earth, providing unique habitats where organisms had to adapt to both aquatic and terrestrial conditions. But how did Earth come to have such a large moon? The leading theory, supported by considerable evidence, is called the giant impact hypothesis. According to this theory, about 4.5 billion years ago, when Earth was still very young, barely 50 million years after the solar system began to form, a Mars-sized object, sometimes called Theia, collided with the proto-Earth in a catastrophic impact. The collision was staggeringly violent, with enough energy to vaporize parts of both bodies and to melt the entire surface of Earth. Debris from both Earth and Theia was ejected into orbit around Earth, forming a ring of molten rock and vaporized material. Over time, this debris cooled and coalesced, pulled together by gravity, eventually forming the Moon. This theory explains many puzzling features of the Earth. Moon system. Why the Moon has a relatively small iron core compared to Earth. Why moon rocks have compositions similar to Earth's mantle material. And why the Moon is relatively depleted in volatile elements that would have been vaporized in such a hot, violent event. If you imagine that titanic collision, two planetary bodies smashing together with unimaginable force, the sky filled with glowing debris, oceans of molten rock, and then, from that chaos, the gradual formation of our Moon, you gain a sense of the violent and dramatic processes that shaped our cosmic home in its earliest days. You need to add some text for me to talk. Let's turn our attention now to the planet Uranus, a world that rolls through space in a most unusual manner. While most planets in our solar system spin on an axis that's roughly perpendicular to their orbital plane, tilted by modest amounts, Uranus is tilted on its side by approximately 98 degrees. Imagine a planet lying on its side as it orbits the Sun, its north and south poles pointing almost directly at the Sun at different points in its orbit, and you'll have a picture of Uranus. This extreme axial tilt means that Uranus experiences the most extreme seasons of any planet in our solar system. Each pole gets around 42 years of continuous sunlight, followed by 42 years of continuous darkness, because Uranus takes 84 Earth years to complete one orbit around the Sun. Picture living on Uranus, if such a thing were possible, and experiencing a summer that lasted for 4 decades with the Sun circling endlessly around the sky, never setting, followed by a winter equally long where the Sun never rises and darkness reigns for 42 years. The equatorial regions would experience a rapid day-night cycle as the planet rotates once every 17 hours. But they would also experience subtle seasonal changes as different parts of the planet tilt toward or away from the distant Sun. Scientists believe that Uranus acquired this unusual tilt early in the solar system's history, likely the result of one or more massive collisions with Earth-sized objects during the chaotic period of planetary formation. The impact or impacts were violent enough to knock the entire planet onto its side, and it has remained in that orientation ever since. A testament to the turbulent early days of our solar system, when collisions between planetary bodies were common, and the architecture of the planets was still being determined by gravitational interactions and catastrophic impacts. Now, allow your mind to wander to one of the most volcanically active bodies in our entire solar system, Jupiter's moon, Io. While Earth has perhaps 50 to 60 volcanoes that erupt in any given year, and most moons and planets in our solar system show little or no current volcanic activity, Io is in a constant state of eruption, with hundreds of active volcanoes covering its surface. If you could observe Io for just a few hours, you would likely witness multiple volcanic eruptions in progress, with fountains of lava shooting hundreds of kilometers into space and massive lava flows spreading across the surface. Some of Io's volcanic plumes can reach heights of up to 500 kilometers above the surface, erupting with such force that material is ejected into space and either falls back to the surface or escapes into orbit around Jupiter. The reason for this extreme volcanic activity is the same process that heats Europa's subsurface ocean: tidal heating. Io orbits Jupiter at a distance of about 422,000 kilometers, well within the powerful grip of Jupiter's gravity. But Io's orbit is not perfectly circular. It's slightly elliptical due to gravitational interactions with Europa and Ganymede, the other large moons of Jupiter. As Io moves closer to and farther from Jupiter in its elliptical orbit, the immense gravitational force of Jupiter flexes and squeezes Io like a rubber ball being rhythmically compressed and released. This constant flexing generates tremendous heat through friction in Io's interior, enough heat to keep much of the interior molten and to drive continuous volcanic activity across the surface. The result is a world unlike any other we know, a moon covered in volcanic calderas, lava lakes, and vast plains of sulfur and sulfur dioxide frost, painted in vivid yellows, oranges, reds, and blacks. Io has essentially turned itself inside out through volcanic activity multiple times over its history, with volcanic eruptions constantly resurfacing the moon and burying impact craters almost as soon as they form. This is why Io has the youngest surface of any solid body in the solar system, constantly renewed by volcanic activity, a reminder of the powerful forces that shape worlds throughout our cosmic neighborhood. Consider for a moment the concept of the habitable zone, sometimes called the Goldilocks zone, the region around a star where conditions might be just right for liquid water to exist on a planet's surface. For our solar system, this zone extends roughly from about 0.95 AU to about 1.37 AU from the Sun. Earth at 1 AU sits comfortably within this zone, and Mars at about 1.5 AU sits near its outer edge. Venus at about 0.7 AU is too close to the Sun, receiving too much solar energy for liquid water to remain stable on its surface. The concept seems simple enough: too close to the star, and water boils away; too far, and water freezes. But the reality is considerably more complex and nuanced. The habitable zone depends on many factors beyond just distance from the star, including the planet's atmosphere and its composition, the planet's geological activity, the presence of a magnetic field, and even the planet's history. Venus, for example, might once have had liquid water on its surface early in its history, before a runaway greenhouse effect transformed it into the hellish world we observe today. Mars, sitting near the outer edge of the habitable zone, likely had liquid water flowing on its surface billions of years ago when it had a thicker atmosphere, but lost most of that atmosphere over time and is now a frozen desert. And then there are the possibilities we've discussed. Moons like Europa and Enceladus, with subsurface oceans heated by tidal forces existing far outside the traditional habitable zone, yet potentially harboring the conditions necessary for life. These discoveries have expanded our understanding of where life might exist, suggesting that the habitable zone is not a rigid boundary, but rather a guideline, and that life might find ways to thrive in environments we once thought impossible. As you contemplate this, imagine the diversity of worlds that might exist throughout our galaxy, some similar to Earth, orbiting their stars at just the right distance, others like Europa, frozen on the outside but harboring warm oceans within, and perhaps even stranger environments we haven't yet imagined, all potentially hosting their own unique forms of life. Let us turn now to a remarkable feature of our solar system that you might not have considered: the solar wind. The sun doesn't just emit light and heat, it also constantly streams particles out into space. A flow of charged particles, primarily electrons and protons, that rushes outward from the sun's corona at speeds of about 400 to 800 kilometers per second. This solar wind fills the entire solar system, creating what scientists call the heliosphere, a vast bubble of solar influence that extends far beyond the orbits of the planets. The solar wind is not uniform. It varies in intensity depending on solar activity, and it carries with it the sun's magnetic field, which becomes twisted and stretched as it extends outward into space. When the solar wind encounters a planet with a magnetic field, like Earth, it interacts with that field in fascinating ways. Earth's magnetic field acts like a protective shield, deflecting most of the solar wind around the planet and preventing it from stripping away our atmosphere. But some particles from the solar wind get funneled along Earth's magnetic field lines toward the poles, where they collide with atoms and molecules in the upper atmosphere, causing them to glow with beautiful shimmering colors. These are the auroras, the northern and southern lights, those ethereal curtains of green, red, and purple light that dance across polar skies. The colors depend on which atmospheric gases are being excited. Oxygen produces green and red light. Nitrogen produces blue and purple. The intensity of auroral displays varies with solar activity, becoming more frequent and spectacular during periods of high solar activity when the sun releases bursts of particles in events called coronal mass ejections. But planets without magnetic fields, like Mars and Venus, have no such protection from the solar wind. Over billions of years, the solar wind has gradually stripped away much of Mars's atmosphere, transforming it from a world that might once have been warm and wet into the cold, thin atmosphere desert we see today. The solar wind extends outward until it finally encounters the interstellar medium, the sparse gas and dust that exists between stars, creating a boundary called the heliopause. This is the region that Voyager 1 crossed in 2012, officially entering interstellar space, though, as we discussed, it remains within the sun's gravitational influence. The heliosphere, shaped somewhat like a comet with a rounded front and a long tail streaming behind as the sun moves through the galaxy is our solar system's bubble in space, the region where the sun's influence dominates over the interstellar environment. Drift with me now to consider comets, those icy wanderers that occasionally visit the inner solar system, trailing long, glowing tails behind them. Comets are often described as dirty snowballs, chunks of ice mixed with dust and rocky material left over from the formation of the solar system 4.6 billion years ago. Most comets spend the majority of their time in the cold outer reaches of the solar system, in the Kuiper belt or the even more distant Oort cloud, where temperatures are so low that their ices remain frozen and stable. But occasionally, gravitational perturbations from passing stars or from the giant planets can nudge a comet's orbit, sending it falling inward toward the sun. As a comet approaches the inner solar system and the sun's warmth begins to affect it, something magical happens. The ice on the comet's surface begins to sublimate, turning directly from solid to gas without passing through a liquid phase, because the vacuum of space provides no pressure to allow liquid water to exist. This sublimating ice carries dust particles with it, creating a cloud of gas and dust around the comet's nucleus called a coma. The coma can grow to be hundreds of thousands of kilometers across, larger than Jupiter, even though the comet's nucleus itself might be only a few kilometers in diameter. The solar wind and radiation pressure from the sun push on this coma, blowing the gas and dust away from the comet and creating the characteristic tails. Comets actually have two tails: a dust tail, composed of small particles that reflect sunlight and often appears yellowish or white, and an ion tail, composed of ionized gas that glows with a bluish color. These tails always point away from the sun, regardless of which direction the comet is moving, because they're pushed by solar radiation and the solar wind. A comet's tails can stretch for millions of kilometers across space, creating one of the most spectacular sights in the solar system. Some comets, called short-period comets, orbit the sun relatively quickly, returning to the inner solar system every few years or decades. The most famous of these is Halley's Comet, which orbits the sun once every 75 to 76 years and has been observed and recorded by humans for more than 2,000 years. Other comets, called long-period comets, have highly elliptical orbits that take them far out into the Oort cloud, and they might take thousands or even millions of years to complete a single orbit. Each time a comet passes through the inner solar system, it loses some of its ice to sublimation, and eventually, after many passages, it can be depleted of volatile materials, leaving behind just a rocky core. Some asteroids we observe today might actually be dead comets, their ice long since evaporated away. Comets are time capsules from the early solar system, preserving materials and conditions from that ancient era, and studying them helps scientists understand how our solar system formed and evolved. Now, let's contemplate the concept of orbital resonance, a beautiful example of gravitational harmony in our solar system. When two orbiting bodies have orbital periods that are related by a simple ratio, they're said to be in orbital resonance. This means that the bodies repeatedly return to the same relative positions at regular intervals, and their gravitational interactions reinforce each other over time. One of the most striking examples of orbital resonance in our solar system involves Jupiter and its moons. Three of Jupiter's largest moons, Io, Europa, and Ganymede are locked in what's called a Laplace resonance. For every orbit that Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4 orbits. This 4:2:1 ratio means that these moons regularly align in specific configurations, and their gravitational tugs on each other maintain this precise relationship. This resonance is not just a mathematical curiosity, it has profound physical effects. The resonance keeps Io's orbit slightly elliptical, which, as we discussed earlier, leads to the tidal heating that drives Io's extreme volcanic activity. Similarly, the resonance contributes to the tidal heating that maintains Europa's subsurface ocean. Without this resonance, these moons' orbits would gradually become more circular due to tidal interactions with Jupiter. The tidal heating would decrease, and Io might become volcanically dead, while Europa's ocean might freeze solid. Orbital resonances appear throughout the solar system. Neptune and Pluto are in a 3:2 resonance, meaning that for every 3 orbits Neptune completes, Pluto completes exactly 2. This resonance actually protects Pluto from ever having a close encounter with Neptune, even though Pluto's elliptical orbit sometimes brings it closer to the Sun than Neptune. The resonance ensures that whenever Pluto crosses Neptune's orbital distance, Neptune is always far away on the other side of the Sun. Even the rings of Saturn show resonances, with gaps in the rings appearing at locations where ring particles would be in resonance with Saturn's moons. These gaps, called the Cassini division and other features, occur because particles in those locations receive repeated gravitational tugs from moons that gradually clear them out of those regions. Orbital resonances remind us that the solar system is not just a collection of objects moving independently through space, but rather an interconnected system where everything influences everything else through the invisible hand of gravity, creating patterns and relationships of mathematical beauty. You need to add some text for me to talk. Let your thoughts drift now to Saturn's moon, Enceladus, a small, icy world that has surprised scientists with its remarkable activity. Enceladus is only about 500 kilometers in diameter, small enough to fit within the borders of Arizona, and at first glance, it might seem like just another frozen moon in the outer solar system. But in 2005, when the Cassini spacecraft flew past Enceladus, it discovered something extraordinary: enormous geysers of water ice and vapor erupting from cracks near the moon's south pole, shooting hundreds of kilometers into space. These geysers, emerging from fractures that scientists have nicknamed tiger stripes because of their appearance, are evidence that beneath Enceladus's icy crust lies yet another subsurface ocean of liquid water. Like Europa and Io, Enceladus is heated by tidal forces, though in this case the interaction is between Enceladus and Saturn, along with orbital resonances with other moons. This tidal heating keeps an ocean of liquid water warm beneath the ice, and this ocean is in contact with a rocky core. When Cassini flew through the geyser plumes, instruments analyzed their composition and found not just water, but also organic molecules, salts, and even molecular hydrogen, which on Earth is often produced by hydrothermal reactions between hot water and rock. This suggests that Enceladus might have hydrothermal vents on its ocean floor, similar to the vents found in Earth's deep oceans, which on our planet support entire ecosystems of life forms that don't depend on sunlight, but instead derive energy from the chemical reactions occurring at these vents. The discovery of molecular hydrogen is particularly exciting because it represents a potential energy source for microbial life. On Earth, many microorganisms use reactions between hydrogen and carbon dioxide to generate energy. The fact that Enceladus is actively venting material from its subsurface ocean into space makes it an ideal target for searching for signs of life, because a spacecraft could fly through the plumes and collect samples without even needing to land on the surface. The material in the plumes eventually falls back to Enceladus or escapes to form one of Saturn's rings, the E-ring, a tenuous ring of tiny ice particles that extends from Enceladus's orbit outward, fed by the moon's cryovolcanic activity. Imagine this small moon so far from the sun that solar energy is negligible, yet active and dynamic, with an ocean that might harbor life, continuously spraying its ocean into space for us to sample. Consider now the rotation of the sun itself, because even our star has some surprising characteristics. The sun doesn't rotate as a solid body because it's not solid at all, but rather a ball of plasma, gas so hot that electrons are stripped from atoms. Different parts of the sun rotate at different speeds, a phenomenon called differential rotation. At the sun's equator, the rotation period is about 25 days, meaning the equatorial regions complete one full rotation every 25 days. But as you move toward the sun's poles, the rotation period becomes longer, stretching to about 35 days at the poles. This means the sun's equator is rotating faster than its polar regions, and this differential rotation plays a crucial role in generating the sun's magnetic field. The sun's magnetic field is not simple and stable like a bar magnet, but rather complex and dynamic, constantly changing and evolving. The differential rotation, combined with convection currents in the sun's interior, where hot plasma rises and cooler plasma sinks, twists and tangles the magnetic field lines, creating a magnetic dynamo. Over time, these magnetic field lines become increasingly twisted and tangled, emerging from the sun's surface as sunspots, dark regions that appear dark only because they're slightly cooler than their surroundings, about 4,000 Kelvin, compared to the surrounding surface temperature of about 5,800 Kelvin. Sunspots often appear in pairs or groups, and they mark places where strong magnetic fields emerge from the sun's interior. The number of sunspots on the sun's surface varies in a regular cycle called the solar cycle, which lasts approximately 11 years. During solar maximum, the sun might have dozens or even hundreds of sunspots, frequent solar flares, and coronal mass ejections. During solar minimum, the sun might go days or weeks without any visible sunspots. The solar cycle influences space weather throughout the solar system, affecting satellite operations, communications, power grids on Earth, and the intensity of auroral displays. Interestingly, at the peak of each 11-year cycle, the sun's magnetic field flips, with the north and south magnetic poles switching places. This means the complete magnetic cycle is actually about 22 years long. Two 11-year sunspot cycles tile. Scientists still don't fully understand all the details of how the sun's magnetic field is generated and why the cycle has the length it does, making solar physics an active area of research. Let us drift outward now to contemplate Pluto, that distant world that has captured public imagination and affection despite being reclassified from planet to dwarf planet in 2006. Pluto orbits the Sun at an average distance of about 39 AU, though its highly elliptical orbit brings it as close as about 29 AU and takes it as far as about 49 AU from the Sun. At these distances, the Sun appears merely as a very bright star, and sunlight takes more than 5 hours to reach Pluto's surface. For most of the 20th century, Pluto was the only known object in the outer solar system beyond Neptune, discovered in 1930 by Clyde Tombaugh. But starting in the 1990s, astronomers began discovering other objects in similar orbits, revealing that Pluto is actually part of a vast population of icy bodies called the Kuiper Belt. Some of these objects are comparable in size to Pluto or even larger, such as Eris, which is about the same size as Pluto and slightly more massive. This discovery led to the debate about what constitutes a planet, and ultimately to the definition adopted in 2006 that classified Pluto as a dwarf planet. But regardless of classification, Pluto is a fascinating world. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more complex and geologically active than anyone expected. Instead of a dead, cratered ball of ice, New Horizons showed us a world with vast nitrogen ice plains, water ice mountains rising several kilometers high, possible cryovolcanoes, and a thin atmosphere of nitrogen with traces of methane and carbon monoxide. Pluto's surface shows evidence of recent geological activity, meaning activity within the last few 100 million years or less, which is remarkably young for such a small, distant world. The source of this geological activity remains mysterious because Pluto is too small and too far from other large bodies to be significantly heated by tidal forces. Some scientists speculate that radioactive decay in Pluto's core might provide enough heat, or that Pluto might have had a warmer past and is only now slowly freezing solid. Pluto also has 5 known moons, the largest of which, Charon, is about half Pluto's diameter, making the Pluto-Charon system almost a double dwarf planet. Pluto and Charon are tidally locked to each other, meaning they always show the same face to each other as they orbit their common center of mass. From Pluto's surface, Charon would hang motionless in the sky, never rising or setting, always in the same position. The New Horizons mission transformed our understanding of Pluto, showing us that even in the cold, dark outer reaches of our solar system, worlds can be dynamic, complex, and beautiful. Now, allow your mind to contemplate the nature of gas giant planets, those massive worlds composed primarily of hydrogen and helium with no solid surface. Jupiter, Saturn, Uranus, and Neptune are fundamentally different from the rocky planets of the inner solar system. If you could somehow descend into Jupiter's atmosphere, you would find that there's no clear boundary between atmosphere and interior. Instead, as you descended deeper, the atmospheric pressure would gradually increase, and the hydrogen gas would become denser and denser, eventually transitioning to a liquid state without any discrete surface. Deeper still, under immense pressure and temperature, the hydrogen would take on exotic properties, forming what's called metallic hydrogen, a state of matter where hydrogen behaves like a liquid metal and can conduct electricity. Scientists believe that Jupiter has a layer of metallic hydrogen thousands of kilometers thick surrounding its core, and it's the circulation of this metallic hydrogen that generates Jupiter's powerful magnetic field, the strongest planetary magnetic field in the solar system, about 20,000 times stronger than Earth's. Even deeper, at Jupiter's center, there may be a rocky core with a mass perhaps 10 to 20 times Earth's mass, compressed under pressures millions of times. Earth's atmospheric pressure and heated to temperatures of perhaps 36,000 Kelvin, hotter than the surface of the Sun. But this core, if it exists, is not like the solid rock we're familiar with. Under such extreme conditions, materials behave in ways that are difficult to imagine and challenging to study, even in laboratory settings. The gas giants give us a window into extreme states of matter and physics, conditions that don't exist anywhere on Earth but that are common throughout the universe, since most exoplanets discovered around other stars are Jupiter-sized or larger. Understanding these massive planets helps us understand not just our own solar system, but planetary systems throughout the galaxy. Consider the asteroid Vesta, one of the largest objects in the asteroid belt, and a world with a surprising amount of geological diversity for such a small body. Vesta has a diameter of about 525 kilometers, making it about the size of Arizona, and it's the second most massive object in the asteroid belt after the dwarf planet Ceres. What makes Vesta particularly interesting is that it's one of the few asteroids that underwent differentiation, the process by which a planetary body separates into distinct layers, with heavy elements like iron sinking to form a core and lighter materials rising to form a mantle and crust. This process requires enough heat to partially or completely melt the body's interior. And for most asteroids, which formed in the relatively cool environment of the asteroid belt, this never happened. But Vesta was heated, likely by the decay of radioactive elements that were common in the early solar system. And it developed an iron core, a rocky mantle, and a basaltic crust, making it structured somewhat like a miniature terrestrial planet. When the Dawn spacecraft orbited Vesta from 2011 to 2012, it revealed a world with a rich geological history, including ancient lava flows, impact craters, and one particularly massive crater near Vesta's south pole that's so large and deep that it exposed material from Vesta's interior. This impact was so violent that it sent fragments of Vesta flying into space, some of which eventually made their way to Earth as meteorites. In fact, scientists had been studying a particular class of meteorites called HED meteorites, Howardites, Eucrites, and Diogenites for decades before the connection to Vesta was confirmed. These meteorites are pieces of Vesta that we can hold in our hands, fragments of an asteroid's crust and mantle that tell us about conditions in the early solar system. Vesta represents a fascinating middle ground between small, primitive asteroids that have remained largely unchanged since the solar system's formation, and large planets that have undergone extensive geological evolution. It's a window into the planet formation process, showing us what the building blocks of terrestrial planets might have looked like in the early days of our cosmic neighborhood. Let's turn our attention to the solar system's formation itself, to understand how all these worlds we've been discussing came to exist. About 4.6 billion years ago, in a spiral arm of the Milky Way galaxy, there was a large cloud of gas and dust called a molecular cloud or nebula. This cloud was mostly hydrogen and helium left over from the Big Bang, but it also contained heavier elements forged in previous generations of stars and scattered into space when those stars died. Something happened to disturb this cloud, perhaps the shock wave from a nearby supernova explosion, and this disturbance caused part of the cloud to begin collapsing under its own gravity. As the cloud collapsed, it began to spin, and conservation of angular momentum caused it to spin faster and faster, much like an ice skater spins faster when they pull their arms in. The collapsing cloud flattened into a disk, with most of the mass concentrating in the center, where it became denser and hotter. Eventually, the center became so hot and dense that nuclear fusion ignited and our sun was born. But not all the material fell into the sun. The remaining gas and dust in the surrounding disk began to clump together through a process called accretion. Tiny particles stuck together through static electricity and chemical bonds, forming larger and larger clumps. These clumps collided and merged, growing into objects called planetesimals, ranging from meters to kilometers in size. The planetesimals, in turn, collided and grew into protoplanets and eventually into the planets we see today. This process didn't happen uniformly throughout the disk. Close to the sun, where temperatures were high, only materials with high melting points, like metals and rocky minerals, could remain solid. This is why the inner planets, Mercury, Venus, Earth, and Mars, are small and rocky. Farther from the sun, beyond what's called the frost line, temperatures were cold enough for volatile materials like water, methane, and ammonia to freeze into ice. These ices were much more abundant than rock and metal, so the planets that formed beyond the frost line could grow much larger. As we approach the end of our journey through the solar system, let's contemplate one final fact. The solar system is ancient, but it's not eternal. Our sun is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. For the next 5 billion years or so, the sun will continue burning hydrogen in its core, remaining relatively stable, though it will gradually grow brighter over this time. But eventually, the hydrogen fuel in the sun's core will run out. When this happens, the sun will begin burning hydrogen in a shell around its core, and this will cause the sun to expand, entering a phase called the red giant phase. The sun will swell in size, becoming perhaps 100 times larger in diameter than it is now, engulfing Mercury, Venus, and possibly Earth. The exact fate of Earth is uncertain, because as the sun expands, it will lose mass through an intense solar wind, and this mass loss will weaken its gravitational hold on the planets, causing their orbits to expand outward. Earth might barely escape being engulfed, or it might not. Either way, Earth's surface will be heated to temperatures of thousands of degrees, vaporizing the oceans, melting the crust, and rendering our planet utterly uninhabitable. After the red giant phase, the sun will eject its outer layers, creating a beautiful planetary nebula, a shell of glowing gas expanding into space, and the sun's core will collapse into a white dwarf, a dense hot remnant about the size of Earth but containing about half the Sun's current mass. The white dwarf will slowly cool over trillions of years, eventually becoming a cold, dark black dwarf. The planets, or whatever remains of them, will continue to orbit this stellar remnant, frozen and dark, illuminated only by the faint light of distant stars. This is the far future of our solar system, billions of years from now, a timescale so vast it's difficult to comprehend. But for now, in this moment, in this cosmic epoch, our solar system is alive with activity, with worlds of ice and fire, with moons that might harbor life, with rings and storms and geysers, with rocks tumbling through space and comets falling toward the sun, with a brilliant star at the center providing warmth and light, and with one small blue world where life has emerged and evolved and learned to look out at the cosmos with wonder. As you rest now, surrounded by the peaceful darkness, remember that you are part of this vast cosmic family, made of elements forged in ancient stars, living on a world that orbits our sun, itself one star among hundreds of billions in our galaxy. You are connected to all of this, to the grandeur and beauty of the cosmos, to the story that began 4.6 billion years ago and continues unfolding all around us. Thank you for listening in. May you rest well, surrounded by the wonders of our cosmic home, and may your dreams be filled with the beauty of distant worlds and the peaceful depths of space. Good night.